this video, we're going to discuss strong acids and bases. Now, strong doesn't mean they're the most dangerous or the most destructive or they react the fastest. Instead, strong is a technical term meaning that they fully dissociate. This just means that when you add a strong acid or base, so HCl, H2SO4, HNO3, so selection of strong acids, or things like NaOH, potassium hydroxide, for some strong bases, when these go into solution, they completely separate into their ions. So you get H plus and Cl minus, or you get two H pluses and a sulfate. For your hydroxides, you get a sodium plus and a hydroxide, or potassium plus and a hydroxide. But these completely break apart. If you started with 100, whatever your starting molecules were, you got that much of your products. Or in the sulfuric acid's cases, I guess 200 H pluses. All of them separate. That is what it means to be a strong acid or base. This is convenient in that it makes calculations with them easy. They're stoichiometric. Whatever amount you have, that's the amount that reacts. So if we have a situation where we had 0.15 liters of 1 molar HCl, and we added 0.14 liters of 0.9 molar sodium hydroxide. So have a strong acid and a strong base reacting. Well, this is HCl plus NaOH. They're going to form NaCl and water. This is the reaction that will occur when these chemicals react, and we just can treat it like stoichiometry. I have two amounts of chemicals, of starting materials, which means one of these is going to be limiting. And so we can use that info to figure out how much product we have or how much leftover starting material we have. In this case, let's find pH after mixing. Well, our HCl, 0.15 liters of HCl solution. For every 1 liter of the HCl solution, there's 1 mole of HCl. So that would be 0.15 mole of HCl to start with. In terms of our hydroxide, I had 0.14 liters of the sodium hydroxide solution. In every 1 liter of the sodium hydroxide solution, there's 0.9 moles of sodium hydroxide, which will be 0.126 mole sodium hydroxide. Well, they're 1-to-1 in my balanced reaction, and so I have less sodium hydroxide. That's my limiting reagent, which means I have leftover HCl. These are going to react with each other. 0.15 mole of HCl, it's going to react to lose 0.126 mole from the sodium hydroxide reacting with it, leaving me with 0.024 mole of HCl left over. All the hydroxide reacts with a good chunk of the HCl, but there's a little bit of HCl left over. Well, that's in solution and can be used to find the pH. That's going to translate into 0.024 mole of H plus, because all of the H plus on HCl will break free. And so we have that much H plus in our volume, 0.024 mole of H plus. Our volume, well, we added these two volumes together, so it should be about 0.29 liters total volume. And so we can find our concentration here. We find that that is 0.08276 molar, which I can take the negative log of to find the pH. What we'll find is that pH is 1.083. Compare that to our starting solutions. Well, 1 molar HCl would have had a pH of approximately 0. And 0.9 molar hydroxide, we can calculate that one out, would have been 0.9 molar hydroxide. Negative log of that will give me the POH, which was 0.045757. And remember that 14 is pH plus POH, so we can solve the pH for that sodium hydroxide solution. Would have been 13.95. So the two original solutions had wildly different pHs. We combined them together, they eliminated some of themselves, there was a little bit left over of the acid, and so we ended up with an acidic final solution. But strong acids and bases can just be calculated stoichiometrically. In the next video, we'll discuss weak acids and bases, where we have to use equilibriums to calculate out the pH, because the chemicals do not fully dissociate.